Welcome back. Let's talk about digital logic. This is a discrete math course, and the Johnson Bot text that we've been using is definitely a math text. However, most of what we've been covering in there has pretty direct applications towards software. That is, we can use it to help us write better code, write programs. This particular unit, digital logic, is a little bit different in that it's has a hardware focus. That is, we're mostly concerned with how to design and eventually fabricate digital circuits that show up in silicon chips, that show up in computers. So that's our primary emphasis and of this unit. And my notes here that I'm just going to kind of go through here and point at, talk about, and draw some pictures. Definitely have a hardware focus from a perspective of designing digital circuits, practical circuits, and the techniques that are used for doing that. Okay, so a little bit of the math background, or starting out with a kind of a math perspective. We can think of these Boolean functions as functions that we've talked about functions in previous units, and Boolean functions are a specific kind of functions that map Boolean values, that is true false values, in the domain back to true false values in the range. So the output is typically a single binary value, but the input can be one binary value. So it map zeros and ones back into zeros and ones, or the input could also be an ordered pair, that is 0 0 or a 0 1 or 1 0 1 1, an ordered pair like that, and map that back into the to a single Boolean value. It could also be a triplet or more, right? So you can have lots of variables on the input side mapping into one single Boolean value on the other side. So for example, you could have a function g with inputs x, y, and z defined by this Boolean equation here. Now here we're using this tick to mean not, and we're using juxtaposition to mean and then we're using this plus symbol to mean or. So it looks a lot like regular algebra, and it has a set of rules we call Boolean logic, many of which are similar to the traditional algebra that you're already familiar with. So this particular Boolean equation consisting of nots, ands, and ors. All right, those are our three primary operators: nots, ands, and ors. Could also be constructed in an actual what we call a gate diagram, which isn't exactly an actual physical circuit, but it's getting there. It's getting closer to how this thing would actually look if it were fabricated on a piece of silicon. I mean, kind of. There's some transformations that are done in here, but this is a level of abstraction that's useful for digital design. And that is, we'll get a design that looks like this, but then we still got to crank on it some more and change it around before we can actually get it onto the silicon. But this gets us largely there. All right, so the operator precedence of these operations kind of shows up in the circuit here. So not has the highest precedence, so we do that first. So we'll take this binary value y and put it in a not gate, and then this and operation that has the next highest precedence. So we'll take the output of the y gate of the not gate and combine that with the x and put those into an and gate, and then we'll take that result and we'll OR it with z. So we're doing the not first, then we're doing the and next, and then we're doing the OR last. So these are the rules of precedence, which are similar to the rules of regular algebra. In regular algebra, of course, this reminds you of addition, and of course, this would be like multiplication, and this would be kind of exponentiation. So similar precedence rules. But once again, here we're doing not, then we're doing and, then we're doing or. In other words, we sometimes use the term product for this XY thing and sum for this OR thing. Even though we're not doing multiplication and addition, we're doing and OR, but we still use the terms product and sum. Okay, so these are our three gates that we have. We had to have and, or, and not. So more formally, here they are right here. These are our primary gates, and, or, and not. And for any gate, you can represent it in three ways. You can represent it as a gate diagram, as a algebraic expression, and as a truth table. So there's not, and, or. And here for not, here's the Boolean algebra representation. We use a little tick to indicate not. Here's the gate diagram, and then here's the truth table. Now, we've seen truth tables before in the other sections on logic, but you know, real quick, a truth table just defines what the output's going to be for any given input. So a not gate is a unary gate. It only has one operand. So if that operand is 0, then the output will be 1, and if that operand is the input operand is 1, then the output will be 0. So it just basically flips. You know, you put a 0 in, you get a 1 out. You put a 1 in, you get a 0 out. Okay, and is a binary operation. There's two operands, and if you put two zeros in, you get a 0 out. You put a 0 and a 1 in, you get a 0 out. A 1 and a 0 gets you a 0 out. A 1 and a 1 gives you a 1 out. So we've seen this before. So and is sometimes said as the output of an AND gate will be 1 if both inputs are 1. Otherwise, the output will be 0. It's a way to say it in kind of one sentence. So here's OR. So we use this little symbol for AND, we use this little symbol for OR. So once again, we can represent a gate using three representations: the Boolean algebra, the truth table, and the OR gate. Now, these operations, the values of the truth table, they're defined. We're basically starting with this as a definition, an axiomatic kind of a, you know, start here kind of a thing. The input side is the same for all of these operations. You're basically counting in binary from 0 to however many rows you got. In this case, we're counting to 3, right? 0, 1, 2, 3 in binary. It's the same over here, 0, 1, 2, 3. The only thing that's different is the output column. The AND gate has 0, 0, 0, 1, and the OR gate has 0, 1, 1, 1. Okay, so these are basically the definitions of AND, OR, and NOT, and it basically forms our starting point. So now that we have these three gates defined, we can combine them in different ways and get what are essentially digital circuits. It's just sometimes those circuits are represented in different ways. So here we could have this. This is just an arbitrary combination of operations. So we have a function f that's has inputs a, b, and c, and we're ANDing a and b, and then we're taking that result because a b has precedence. So we're taking that result and ORing that with C. So we could represent it algebraically like this. We could build it, so to speak, at the gate level abstraction, like like this. So we're doing the A and B, ANDing that first, and we're getting we sometimes use the term signal. We're getting a signal out of this thing, the signal AB. We're taking that signal and combining it with C here, and so we get the output F, which is A, B, or C. So the three representations, the Boolean algebra, the gate diagram, and there's also a truth table representation, which would be this. So the truth table representation, you have inputs on this side, and then outputs on this side, and these outputs are in this particular truth table. I've defined a column for each signal, each wire in the diagram, or each intermediate result. Okay, like AB is an intermediate result, an intermediate signal on a wire, all right, between these two devices. Okay, the input side, in this case, we're just counting from 0 to 7 in binary, right? 0, 0, 0 to 1, 1, 1 in binary. And then we have the values of the intermediate, columns that we've calculated here. So AB, we've just taken AB here and applied our definition of AND from the the table on the table on the previous page. So basically, we're looking for two ones. So that happens here, right? 1, 1. so there'll be a 1 in the AB column. And then it happens again here, 1, 1, so there'll be a 1 in the AB column. The rest of the time it's 0. Because that gives you AB. Then to do this to do this OR, you take the AB and combine that with C. So we're looking at these two columns, you know, the AB column and the C column. And in this case, we're looking for at least 1, 1. At least, you know, 1 or more 1s, right? So here's a 1 on C, so we got a 1 there. There's a 1 there, you know, so we got a 1 here, so we got a 1 here and here, so we got 1s there. Okay, so that's the final output, F. So we basically define for any possible 3-bit input of this function. So this is mapping a triplet, right? This function is mapping a triplet of binaries, A, B, and C triplet, back into a single Boolean value output. But we basically, this table's defining for any possible 3-bit input, these are the single bit output that this guy will produce. Okay, so kind of what we did is we started with a Boolean equation. It's just sort of a random, you know, arbitrary equation, and then we drew the gate diagram. Now the translation from Boolean algebra to gate diagram, you're sort of expected to be able to do that. You know, it might take you a little bit of process, but a little bit of practice. But essentially, you can, you know, you can develop the ability to go back and forth between the algebra and the gate diagram, kind of directly. Building the truth table takes a little more work, but you can still start with a gate diagram or an equation for that matter and construct the table column by column. Okay, so starting with equation and diagram, really, because we can go back and forth with those. We start there and then we construct the table. That's so far that's the process we're following. Right, so here's another example that's just a little bit more complicated. We're starting with this arbitrary Boolean expression. We've got, we've got an OR gate in here. We're ORing A and B. Then we're ANDing A and B, and then we're taking those two results and ANDing them together. And then we go over here and we take the C and NOT it first. Then we'll AND that with A. Then we'll take that combined result and OR it with the stuff on the left over here. So if you drew a gate diagram, it would kind of look like this. So this is the kind of thing that you're supposed to be able to go back and forth with. And let's just kind of walk through it. Let's see, where should we start? So we need A or B. We're getting that here, right? Here's the OR gate. We're taking A and B into this OR gate. So we're getting the signal A or B out. Then we need A and B. So we're peeling off A and B off of these two wires here, putting that into an AND gate. We get the signal AB out. Then we need to AND those two guys together. That's happening here. Right, we're taking this guy, and we're putting them together, and we're getting this guy out. Then we need this stuff over here, so we do the C first, NOT it first. Take that result, or that signal on this wire, and combine it with A over here. That's the AC naught thing. So here we got AC naught coming out of this AND gate, and then we'll lastly do this. We'll do this OR here, which is this gate, and we get the final signal. Okay, so you can sort of, go back and forth between this. Takes a little bit of practice. And then we want to know for any given 3-bit input, what's the single bit output going to be on this thing. So for that, you got to kind of construct the table column by column, which I don't think I'll do right now, but that's what you got to do. Though there's more columns in here because there's more intermediate signals in this guy. But still, you start with, so far you're starting with the algebra and then the gate diagram, which are kind of the same, very, very similar thing. And then from that, you construct the truth table. All right, so this guy has, how many gates does this guy have? Let's count them up, okay? That's got 1, 2, 3, 4, 5, 6 gates. So that's 6 electronic devices, that each one of those devices costs money, takes space, uses heat, takes time to process. So if we could produce this output that we want, this F column with less gates, then that would be awesome, right? It would use less space, it would use less heat, less energy, it would process faster. So, we want that. So we want to be able to simplify this this Boolean algebra expression down. And for that, we have something called Boolean algebra, right? So Boolean algebra is it's kind of like regular algebra, regular I want to say arithmetic algebra. And by regular algebra, I mean the kind of algebra that you use on regular numbers, like 7 and like 4 and 42 and stuff. If you want to add them and divide them, that's regular algebra. This is Boolean algebra. It operates only on zeros and ones, 0 being false, 1 being true. Now, any algebraic system has starting point, right? It has what we call identities that define the rules of algebra. Now, Boolean algebra is the same way, and most of these identities are very similar to what you're used to seeing in regular algebra. It's a few of them are different. So once again, we're talking about Boolean algebra. This is not regular algebra, but this guy here, take this guy for example, it makes sense from a regular algebra perspective, right? If you're talking about addition, actually, adding numbers together, then any number plus 0 is that number, right? So it works, but this guy also works with Boolean algebra. It's saying that any true-false value ORed with false is going to be that true-false value. And we can prove that with a little truth table real quick. So, here's OR. OR is, here's the input side of OR. And the output side of OR is this. So what we're saying with this identity here, x or 0 is x, we're saying that if, let's say we make one side x, and then we want to OR that with 0. So basically cross out this row and this row. So we're saying the other operand can only be 0. So we're only interested in these two rows. So x can be 0, x could be 1, but the other side's always going to be 0. So if that's the case, then if x is 0, you get a 0, and if x is 1, you get a 1. So that's what this is saying. If x is 0 here, you're going to get a 0, and if x is 1 here, you're going to get a 1. Okay, so you can prove this kind of like that. You could prove AND the same way. So here's the definition of AND. First, the input side, then the output side. The output side of AND is this. So if we make x this, then we're saying we're ANDing x with 1. So let's cross out the rows where the other operand is 0. Cross out these two rows. So if x is 0, you get a 0. If x is 1, you get a 1, which is, whatever x is going in, that's what's going to come out. That's what this is saying. So, it works. Okay, so very important to realize we're not using regular algebra, quote, quote, air quotes. We're using Boolean algebra. The rules, many of them seem the same, but they're not exactly the same. Now, you could go through and prove these using truth tables if you want, but I'm not going to do that right here. Okay, now most of these kind of look familiar. There's commutative, so you can flip x and y around. There's associative. Then there's the three that are kind of unique are, well, there's two versions of De Morgan's, which we're going to see later. Those are kind of unique to Boolean algebra. And then there's this version of distributed, this identity 15. It's a little bit weird. Back up a little bit to this version of the distributed property. This is similar to so-called regular algebra. Like here, you can take this x and you can factor it into the sum, right? So you can move the x inside. It'll be x times y and then x times z. So x times y, then x times z. So you're probably comfortable with that from regular algebra, but we have a distributive identity for ORing as well for this plus symbol, which means OR, but we sort of it's analogous to addition. Okay, so we have this distributed property for addition as well. So we can OR in the x into the product over here, or into and. So we can take this x and put it in here. So it'd be x or y and x or z, or right here, x or y and x or z. Okay, so this is different. And this one, when you're doing Boolean algebra, you typically forget to even use it because it's so unusual, but it can be very handy for simplification. It is a little weird looking, so just keep that in mind. And all of these, including this one, you could prove with by constructing a truth table similar to this. You could prove that they're true. All right, so in this unit, we're mostly concerned with building the circuits, and we want to take some circuit and see if we can simplify it so we can construct it using less gates. So let's do that. Let's take this guy right here, because this thing is saying that this equation here can be simplified via these identities down to this one, which would be great, right? Because how many gates are in this guy here? Well, there's a NOT gate, so that's one. Then there's two ORs, and then there's an AND gate. So there's 1, 2, 3, 4 gates in here. And what we're saying is we can build this thing with one gate. In other words, let's see, I could draw this just real quick. I could show you another way to draw these guys. So you draw this little figure, and the nice thing about this is you have the two inputs x and y, and then you have their knots. So if you need an x, you can peel it off. If you need an x naught, you can peel it off. So then we can build, let's build this x or y. So we need an x and we need a y. So there's our x and our y, and then we need to OR those together for this OR gate right here. Pardon my crummy looking OR gate. Then over here we need an x and a y naught. So we can peel the x off of here, and then we can get the y naught off of this signal here, this signal with the NOT gate on it. And we can OR those two together. Okay, so coming off of here we've got x or y. Coming off of here we've got x or y naught. We can take these two and AND them together. That's this right here. Okay, so there's 1, 2, 3, 4 gates. We don't need this one, but this is a nice, kind of a clean way to draw gate diagrams. But of course, in this case, we don't really need x. But still, it's 4 gates that we actually need. So what this simplification is saying is that all we need is x, right? That instead of building this with 4 gates and taking up a lot of time, we could just have a wire. Just have the whatever 0 or 1 is coming in. That's what comes out. 0 gates, right? 0. It's much better than 4, right? Like way better than 4. Like this uses some amount of electricity. This uses like no electricity. Okay, so it's way better. So we could prove this, I guess. We could walk through it because it does use our weirdo distributed property that we were talking about. So here we're using this distributed identity 15. We're using it backwards. We're basically factoring the x out of this thing. So like here, x or y, x or z, we're pulling the x out and kind of collecting the y and z together. So here in that case, we're factoring the x out, and we're collecting the y and the y naught together here. So here's the x and the y naught over here. That's rule 15, the weird version of distributive property that everybody forgets because it's so freaky. Okay, then we can use this rule over here, this rule 8, it's just saying something ANDed with its own not is going to be 0. So these two guys, that's what we got. We got a y ANDed with y not, you know. So something not ANDed with its own not is going to be 0. That's what rule identity 8 says. And then lastly, identity 1 over here. If you OR something with 0, you just get that something. So here we're ORing x with 0, so we just got x. So, okay. So once again, algebraically, we've taken this 4-gate circuit and we've used these identities to reduce that to, in this case, 0 gates, which is way better than 4 gates. All right, so Boolean identities, they're a lot of fun. In this particular unit, what we're mostly concerned with is using them to simplify big equations into smaller equations. There's, on the next page of my notes here, there's a couple more of these guys that I don't think I'm gonna do, but I'm not gonna go through applying the identities. But basically here we've got a bunch of gates, 1, 2, 3 NOT gates, 2 OR gates, and an AND gate, and we can get that down to 3 gates. So, you know, that's the idea with Boolean algebra used to simplify these circuits. All right, so far we've started with a gate, a gate diagram or its equivalent Boolean algebra expression, and we've derived the truth table from that. Okay, that's actually opposite of how this happens in design. In digital circuit design, you almost always start with the truth table, and then from the truth table you define the circuit. So it's backwards of what we've been doing so far, right? So we call that circuit synthesis. There's 2 methodologies for doing this. One is called sum of products, and the other one's called product of sums. Sum of products makes the most sense to me, and I think, to my knowledge, it's the most common method that is used to synthesize Boolean circuits. The other method, the product of sums, is kind of where everything's flipped around. It's kind of upside down. We'll kind of go through that a little bit, but not super lot. So here's the basic idea with product of sums, or also called disjunctive normal form. So here's a real simple truth table just to illustrate the basic idea of sum of products. So you have your input side. We're counting from 0 to 3 in binary, 0, 1, 2, 3 in binary. The output side is it's the output that we want. It's an arbitrary result that we want. But the idea is we start with this truth table, which comes from your boss or something, or it comes from the design situation. We'll look at an example of the full process in a minute, but at this point, just think of this as some f that we want to get. It's sort of given this thing from some situation. All right, so what you do is you look at every row of the output column f, and for every row where the output is 1, you build what's called a min term. Okay, and then you at the end you sum those min terms. So you look at this one here, and because there's a 1 here on f, we need a min term. And the min term is just the inputs, x and y, ANDed together. The only difference between min term and midterm is the nots. So you need a min term on this row, and then you look at the x and y, and they're both 0. And because they're 0, you put a not on here. So I'm skipping the math reasons, the proof of why this works, but it hope you'll see it kind of example. You'll see that it does work, but it kind of makes an intuitive sense when you see the whole thing. Okay, then this guy here, we have a 1 here, so we also need a min term, and then we look at the x's, and there's a 1 and a 0, so the 1 means no not, or do not have a not, and a 0 means we need a not. So the min term is x, y, naught. And then the resultant expression f, which is a function of x and y, is just the sum of these two min terms. We're using the term sum, of course we mean or, and we're using the term product, of course we mean and. Okay, so it's the sum of products, right? Or really the or-ing of a bunch of andings, kind of really, but it's easier to say sum of products. Yeah, so this guy will produce that this truth table here. You could prove it to yourself by building this truth table, starting from this equation and work backwards, and you'll see that you get this guy. So before we move on, this is what we call a sum of products form. It's product plus product, and if there were more inputs, there'd be plus product plus product. There'd be a whole string of them. So this is SOP form, but we can do Boolean algebra, which we were just talking about. We can do these steps of Boolean algebra, and we can get it simpler, is the point. I'm not going to go through the actual steps, but these are various identities that are being applied from that identity table. And in the end, you get one gate, right? You get y and not, which you could, f is y not, basically, which you can see from looking at this, right? Because here's y, or here's the y variable, 0, 1, 0, 1. F is just opposite that, right? 1, 0, 1, 0. It's just y not. So kind of by observation, you could see that this f is just y not. But this is a real tiny little table, and you can't, for large tables, you're not going to be able to directly determine what f is. You need this formal process. Okay, so that's what we call sum of products. This is a good place to introduce something called sigma notation. So for sum of products, we're interested in the rows where f is 1. So we have a notation for that. So this same guy, this same f here, function of x, y, given by this equation, can also be represented down here. We're saying f, the function f, which has inputs x and y, is given by the sum of the min terms on rows 0 and 1. So row 0 in binary has a 1 on it, and row, I'm sorry, I misspoke, rows 0 and 2. So row 0 has a 1 on it, and row 2 has a 1 on it. These two rows have min terms, and those two min terms are summed. Okay, so f is a function of x and y given by the sum of the min terms on rows 0 and 2. Okay, this is sigma notation. Sigma's indicating that we're doing this sum, and it's also called min term notation. Okay, that's the basic idea that's the basic idea of sum of products form, which is used to start with a table and derive an algebraic expression from that. Okay, we also have its dual, you might say, called the product of sums. So it's a similar process, but everything's flipped. Okay, so instead of min terms, we have max terms. Instead of looking for ones, we're looking for zeros. Instead of nodding when we see the 0, we're nodding when we see the 1. Okay, it's kind of like upside down world. Everything's backwards. That's conjunctive normal form. Sorry. I can arrange this stuff here. What do we got? Conjunctive normal. Hey, there it is. So we're looking for zeros. There's a 0. There's a 0 on the output column, the F column. When we have a 0, we want a max term. The max terms are the ORs. okay, of both of the inputs. And the knots show up when there's ones on the input. So there's a 1 on the Y, so there's a knot here, which you can barely see. There's a 1 on the X and Y, so there's 2 knots here. Okay. This little scribble is this max term, X or Y naught, right? We've got X going in, we've got Y not going in here, right? So there's a min term here, a max term here, and a max term here. We take the product of those two max terms and we have this dude. So these are, this is two different processes to arrive at the same thing. We started with the same truth table here, 1010, 1010. We got two different equations, so we're saying they're the same. And they are, and you could prove that algebraically, which I'm not going to do. But anyway, product of sum and sum of products, two different methodologies. Before we move on, there's notation for this product of sums. It's pi max terms on rows 1 and 3. Okay, so it's just the same way to kind of do this, or a different way to do the same thing. I prefer SOP. SOP is, to me, is way more intuitive. Okay, so one more example of SOP. Okay, let's say you're given this truth table from your boss. Boss comes to you, says, hey, here's a truth table. I want the circuit by Friday afternoon before you go home, before you go on your trip this weekend, right? So given this truth table, give me a circuit that will work that will produce that. All right. So the first thing you do is generate the min terms. So here we're using sum of products. So this is our input side. It's just counting from 0 to 7. This is F that our boss gave us. It's just an arbitrary output, 0, 1, 0, 1, 0, 1, 1, 1, 1. Just arbitrary. We want some gates that'll do this. Okay, so sum of products method, you start with, you look where the F's are 1. So there's a 1 here, and then there's a 1, 1, 1. And for those rows, we need these min terms. Kind of might remind you of validity a little bit in logic, in propositional logic, a little bit, kind of, sort of, but not really. Anyway, so we need a min term here, ABC. We need one here, ABC. We need one here, here, and here, ABC, ABC, ABC. The only thing that's different between these is the knots. And for the knots, we look over here. So there's a 0, 0, 1. So we need not, no not. Right? Then there's not on the first one here. Then for this min term, there's a not in the middle. So you put it on the B. Here, there's just a knot there. You put that there. Here, there's no knots on the last row. So you don't put any knots. Okay, so you get these min terms, and you could also call them products, and then you sum them all together. So A naught, B naught, C, that's this guy. A naught, B, C, that's this guy. A, B naught, C, that's this guy. A, B, C naught, that one. A, B, C, that one. Okay, so this F, which is a function of A, B, C inputs, is given by, this big equation. And it could also be defined, originally, that is the F output column that your boss gave you. He really could have just given you this. That's all this is really, all this min term notation does is basically specify the truth table. It specifies the output of a column. It doesn't tell you the gates that'll make it. It just tells you what the values need to be. It's really the starting point for the truth table. Anyway, it's saying that the sum of the, this f is given by the sum of the minterms on rows 1, 3, 5, 6, and 7. So here's row 1, there's an f, row 3, row 5, 6, and 7. They all have 1s on there. Okay, so wherever there's a 1, you need a minterm. The minterms all look the same except for their knots. Their knots come from looking at the 0s and 1s on the input side. You generate the minterms, you sum them together. Hey, you could probably write a program to do this, huh? That might happen. Okay, so I'm saying that you start with the truth table. Let's back it up even more. In the real world, the scary real world, this is kind of the process that we follow. You have some problem you're trying to solve. You use your brain and Chat GPT and what other AIs are out there. You get to where you can understand it. Okay, that's the part they typically pay humans to do. Just finding a problem and understanding it, and you reduce it to the problem to a truth table, right? Once you have a truth table, you use this typically sum of products to get an equation in sum of products form. Then we can use some Boolean algebra, and there's other simplification techniques. One is called K-maps, which is beyond the scope of this course. It's interesting stuff though, but beyond the scope of this course. There's also something called Quinn-McCluskey algorithm. Those are the two that I'm familiar with. There's probably others. But you use these various simplification techniques, algebra, K-maps, whatnot, to get a equivalent circuit with less gates, because less gates is better than, if you're actually making something physical. Then you turn that into a logic design, and then you get paid in the end. That's what it's all about, right? Getting paid. Okay, once again, there's a lot more once we have the gate diagram or the equations that correspond to the gate diagram. There's a lot more transformations that have to be done before this thing can be printed, or a stereolithography, fabricated onto silicon. But that's the basic process. So let me go through a design that's kind of a real world thing that uses this process I just delineated for you. So here's a complete design. So say your boss comes to you and says, we need a chip, we need a gadget, a digital circuit that will do this, that will create a circuit that will indicate when exactly one of its 3 inputs is 1. For some reason you need this, all right? So we've got 3 inputs, and they can be 0s, they can be 1s, there's basically 7 combinations of inputs that can go in here, right? From 0, 0, 0 to 1, 1, 1, right? So in this case, we want F to light up because exactly one of these 3 wires here is 1. So we want this guy to light up. Okay, so we're detecting when just exactly one of these. So we can turn that into a truth table, right? So these are the 7 possible input combinations of A, B, and C, right? And then we just look at each row, and we find each row that has exactly one input, exactly one on the input. So this row has a 1 on it. This row here has only 1, 1. So we mark that. This guy, right? This row here has exactly 1, 1 right here on the input. So we mark that. The others have 2 or more 1s, so no dice. Okay, so we want this guy, and this guy to light up when we want to detect this input, and this input. Okay, so we started with a problem statement, and then you think about it till you kind of understand it enough to create this table. Once you have this table, we can use sum of products. So we're looking for the 1s. For every row where the output is 1, we need a min term. So we need a min term here, here, and here. Once again, the min terms they all look the same except for their knots. For their knots, you look at the input side. There's a 0 here and a 0 here, so we not there and we not there. Here, there's a 0. There's a 0 here and a 0 here, so we not the A and the C. Okay, we get these 3 min terms. We sum them, and we've got our equation that'll make this dude. Okay, so we started from English. We go to truth table. We go to sum of products. This turns out to take 14 gates if you counted them. We can do a little more algebra. I didn't do a lot of algebra, but you can do a little bit of algebra, and we can get this down to 12 gates by factoring out the A naught. Okay. That's a little better. It'll save a little space. It could be possible maybe we can get this smaller. I didn't try. Okay. So yeah, fewer gates is better. It's less filling. It still tastes great. Uses less space. It uses less energy. It costs less to make. Those are all good things. If you like this stuff, I highly recommend that you take digital logic design. It's more of a hardware design class for computer engineers rather than computer scientist programmer types, but it's really good to understand hardware at a fundamental level. This is equivalent to, last time I checked, CPE 64 at Sac State. And at Davis, there's an upper division version of this that for some strange reason they require calculus. I have no idea why. You don't need it at all. But anyway, a really good class. It's taught here. Okay. All right, so we can make these guys. We can make a circuit and build it. Let's talk about some hardware considerations. Okay, but hardware considerations. That is, when we fabricate this stuff, there's some issues that are going to come up. Okay, first of all, let's understand that there's other kinds of gates that we haven't talked about yet. All right. So besides and, or, and not, there's nor, which is just or with a not on it. So they put this little bubble on the end. This is the symbol for nor, but you can sort of think of it as an or with everything flipped at the end. So instead of the output column of or here, you have those bits reversed. Okay, so we call that nor. We don't have an algebraic symbol for it. We just use parentheses around the or and then stick a not on the end. Okay, so this is just the kind of gate that one could make if one were so inclined. I'll show you why in a minute. Why we might need that. Here's another one. You could make this guy called NAND, which is basically an AND gate with its output knotted. Sometimes the symbol for it is this with a little bubble on the end. Okay, so it's an AND gate with a bubble, and the output column is just the output column for AND, but everything flipped. So instead of 0, 0, 0, 1, we have 1, 1, 1, 0. So this is another kind of gate that could be made, which we'll see later is good, which I'll show you. Another thing you could do is XOR, which is like OR, except the last column is, is 0. So it's looking for when the bits are different, right? So it's looking for these two rows here, because 0 and 1, the bits are different. 1 and 0, the bits are different. So it's indicating those two conditions. This is useful for encryption. I think I might have talked about that earlier in the course. It's useful for detecting overflows on 2's complement addition. It's useful for other things. Okay, so we could make these, right? this is a gate diagram is a particular level of abstraction that is nice because it maps to this to the Boolean algebra. It's a good level to design at. Okay, but in real life, these have to be made out of smaller pieces still, right? In particular, they're made out of something called a transistor. They've been made out of all kinds of stuff in the past, but relays, vacuum tubes, coconuts, all kinds of things you could make these things out of. This thing here, for example, here's a NOT gate. Here's the truth table, 0, 1, 1, 0. Stole this from Computing 101. Here's a transistor. It's a switch. The input here controls the switch part. It basically opens and closes this part of the switch. So there's a voltage here that can either come out or go down the drain, one of the two. So if you close the switch by putting a 1 on here, then the 1 that's over here will go down the drain instead of out. So you'll see a 0 here. So you put a 1 on here, you see a 0. You put a 0 on here, this thing is open and the 1 comes out. So it does the truth table. This you could understand at an even more fundamental level, of course, down to the physics level, but this is kind of the electrical engineer level, and this is the digital designer level, kind of. And then in this class, we're kind of up at the coder level, Here's a NAND gate. Now, the point of showing you this is that NAND can be made out of these two transistors, and that's the fewest transistors that you can use for a binary operation. Not only that, I've been told by people who know more about this than me that not only are these two transistors, not only are there two of these guys, as opposed to say 3 or 4, but these two are actually smaller. There's something about this circuit that I don't understand the lower level electronics of it, but these two transistors can be made very small for a NAND gate. So that's great. There's only 2 transistors and they're small. So this is a great little gate. It takes up very little amount of space. It takes up less space than AND and OR would take up. Unfortunately, well, the situation is we started with AND, OR, and NOT. That's just how we humans think. That's sort of our starting axioms, so to speak. But it turns out that that this is easier. So what can we do about that, right? How can we leverage the fact that NAND gates are so small? Okay, so that brings us to this idea of bubble pushing and universal gates. All right, so there's this concept called a universal set of gates. The idea is, what gates do you need to have in your toolbox so that you can make anything? Okay, well, AND, OR, and NOT are universal because that's what we started with. I mean, that's our starting point. Okay, that's where it goes way back. That's just where we happen to start with. So that's universal basically by definition. But it turns out you don't actually need OR, okay? So you can get by with AND and NOT. And I can prove that. By De Morgan's, let's see. Well, let's do it this way. So X or Y, not. By De Morgan's, this is X or yeah. So if you did this, you basically have X or Y. So this is like De Morgan's, kind of. And then over here, I'm just doing a double knot on this side to get rid of, the knot. Okay, so basically you could make OR using an AND gate and 3 NOT gates. So it takes a lot of space. You know, this is 1 gate. This is 1, 2, 3, 4 gates. But still, you can get by with just AND and NOT. Similarly, you could prove that you could make OR out of, or rather, you could make ANDs out of ORs and NOTs. So all you really need is OR, comma, NOT. Okay, so you could just have these in your toolbox, or you could just have these 2 in your toolbox. You could make anything. You could have these 2 in your toolbox. You can make anything. Turns out all you need is this one. If you were didn't know what to buy and you went to the electronics store and you weren't sure, you could just buy a giant sack full of NAND gates, and you could build anything you want. Okay, turns out that NOR will also do that. I'm going to prove that in a minute, but the idea is this guy is enough. NAND is universal, and combined with the fact that NANDs are small, it makes it a real nice little gate. So there's actually devices called field programmable gate arrays that consist of nothing but NANDs, and you program them. It's not programming like C++. It's basically connecting the wires up between the gates and building a circuit out of. Okay, so given any Boolean equation, any gate diagram, you could construct any kind of circuit. Let's prove that. All right. So let's prove all you need is an AND. So De Morgan's, which I just did a little while ago, is showing that XY product, quantity naught is equivalent to X naught or Y naught, or NAND, really. This is NAND. It's AND. You do the AND first, and then you NOT the result. So there's the AND gate with a bubble, or a NAND gate, in other words. That's the same as doing the NOTs on the input side. So we put the bubbles on the input side and then doing the OR, right? Like here we're doing the NOTs on the input side, right? These 2 guys, and then we're doing the OR. So this is basically a graphical version of De Morgan's rule. So if you believe De Morgan's rule is true, then this is the graphical version. So it's saying that you can build a NAND gate out of ORs and NOTs. Similarly, you can build a NOR gate out of ANDs and NOTs. Yeah, that's that. The other little trick that we can do, we're working towards proving all you need is NAND. But before we get there, we have to look at this other little trick. So consider the following, if you will. Consider this arbitrary collection of ANDs and ORs. It's a 2-level AND OR thing. You're taking A and B and putting them in an AND gate, and you're taking C, D and putting in an AND gate, and you're taking that result and putting it in an OR gate. You could introduce bubbles here, right? Because X is equal to X not. Double negative is you're back to where you started from. So if you put a bubble here, you could cancel it with the bubble here. Okay, you can do that. And you can do that here too. You can put a bubble here and cancel it with the bubble there. And then we just proved up here that this De Morgan's, this thing is equal to NAND. So that means we can replace this thing. There's that same thing again with NAND. So we started out with AND gates and OR gates, and we ended up with just NAND. Okay, so we're getting there. Let's do this consistently to prove that what we started with, AND, OR, and NOT. Remember, AND, OR, and NOT is just kind of axiomatic. It's like, that's where they started. It's like defining addition or something. They just started with these three logic operations, way back in caveman days or something, Boolean days or whatever. So if we can prove that we can make an AND gate out of NAND, and if we can prove that we can make an OR gate out of NAND, and if we can prove that we can make a NOT gate out of NAND, we've basically proved that all we need is NAND. Okay, so let's start with NOT. So here's a NOT gate. Turns out if you take a NAND gate and tie the inputs together, it's going to function like a NOT gate. I could draw this thing. I should draw it a little bigger. So here's AND, or rather NAND. This is NAND. If you put X on both of the inputs, then basically this difference can't happen and this difference can't happen because both of the inputs are the same. They're either both 0 or both 1. That's this tying the X's together here. So if X is 0, you're going to get a 1. So 1, sorry. And if X is 1, you're going to get a 0. So it's behaving like a NOT gate. So this sort of proves that you can build a NOT gate out of NAND. Similarly, you can build an OR gate out of nothing but NANDs. Start with an OR. We'll introduce bubbles on the inputs, and then we'll cancel those bubbles with NOT gates, right? So these NOT gate and the bubble just cancels each other out. Then we can replace this NOT gate with the NAND gate we just proved how to make up here. Do that twice. Replace this thing with its De Morgan's equivalent, which is also a NAND. Okay, and now we've shown that we can build an OR gate from nothing but NANDs. Lastly, we can build an AND gate from NANDs simply by knotting the output and then canceling that with the NOT gate, and then we've just shown up here that we can build a NOT gate out of NAND. So we replace the NOT gate with NAND. So we can build AND out of this combination of two NANDs, basically. So all you need is NANDs. It takes more gates, but those gates are small, and you can build a device that is just a giant array of NANDs. And because if the other advantage of just using an array of NANDs is, let's say you didn't. Let's say you made a device that had, I don't know, a third of this and a third of these and a third of these. What happens when you run out of AND gates? Then you've got OR. You might have unused OR and NOT gates. They're just taking up space. But if you just use nothing but NANDs, you can fill up the chip with at least something, and that can be a more efficient way to do it. Okay, so it's interesting, beyond just the hardware. It's interesting to think that NAND is universal, because we're used as coders, and as humans and whatnot, we're used to thinking in terms of and or not when we write logic expressions and when we do prepositional logic and all of that stuff. It's interesting to think that the only logic operation you need is NAND. Earlier in the semester, we did because and maybe, and that was taking this, I don't want to use the term logic, but that was taking this line of reasoning in the other direction, right? Saying, what if maybe we can add all these crazy, arbitrary logic operations? Well, this discussion is sort of taking this in the totally opposite direction. We're saying all you need is NAND. Bye.